All right, today we're going to wrap up our first chapter of trigonometry by talking a little bit about harmonic motion, simple and damped, and also talk about phase and phase difference. So what is harmonic motion? Well, this is really cool. Periodic behavior that repeats over and over again is really common in nature. If you think about the four seasons, how they rotate on a regular basis, you think about the moon every 28 days, it rotates around the earth. Low tide, high tide, low tide, high tide. Day, night, the earth rotating around the sun. So those are called harmonic motion. Now, populations can increase and decrease as well by a predictable periodic pattern. If the food supply is scarce, you will have fewer in the population. As the population diminishes, the food supply improves. Then your population improves, and then your food supply diminishes, and it repeats over and over and over. Now, other common types of periodic behavior, and this is the one we're going to focus on, involve motion that's caused by vibration or by oscillations. And some of these things could be as simple as taking a spring and putting a mass on it, like a weight, and pulling it down and then let it going, or compressed, which pushed in, and then let it go. And it goes back and forth, up and down. That is simple, what we call simple harmonic motion. You could also take a pendulum and tie it to the ceiling, a string, and tie a baseball at the end of it and swing it. That is simple harmonic motion. Also, which we don't think about this, but sound waves, light waves, AC current, electricity, pulsating stars, to name a few, are also models of periodic behavior called simple harmonic motion. So if we think of simple harmonic motion as sine, then it would just look at it would look like a sine wave, just like the sine graph, just like we've talked about. Now, if you put some strings or a weight on a spring, and we just pull it down, and it goes up and down and up and down and up and down, it's going to model sine. It's literally going to look like a curve like that. Notice that the mass returns to its original position over and over again. Now, this is important, and I've talked about this in class, and I really haven't defined what a cycle is, but a cycle is one complete vibration of an object. So the mass in Figure 2 completes one cycle between O and P. That cycle we also call a period, okay? Or I like to call it T. All right? So now, simple harmonic motion then can be thought of in this manner. We're going to use the same formula that we used before for sine and cosine. A sine, but instead of K, we're going to use the old school omega. That is letter omega. And that makes us know that we're describing displacement of an object. So we actually have something going on, whether it's a sound wave, or it's a oscillating object, like a weight or a pendulum, okay? The amplitude still is A, absolute value of A. The period now is 2 pi over omega, and now we add frequency. So this is just 2 pi over K, by the way, nothing new. It's just that we're calling it omega. But frequency is new, and that's the number of cycles per unit of time, usually called cycles per second is usually the time, which is what we call hertz, Hz, Hertz. And that is the reciprocal of period. So omega over 2 pi is our frequency. So notice that these two functions, a sine 2 pi vt and a cosine 2 pi vt, have frequency of v, because 2 pi v over 2 pi is v. Since we can immediately read the frequency from these equations, we often write the equations of simple harmonic motion in this form. Now, I'm not saying you have to, I'm just saying you can. Okay, so here's the first example. Find the amplitude and period and frequency of the motion of the mass below, or to our right, given by that formula, where y is measured in inches and t in seconds. So the amplitude then is 10. That means it goes 10 above and 10 below, and I forgot something, inches, measured in inches, so 10 inches. So we have the midline, it's going to go 10 above and 10 below from its rest position. The period is 2 pi over 4 pi, which is 1/2. Now the frequency is a reciprocal of period, which is 2. 2 cycles per second, or what we know as hertz, Hz. Oh, I also forgot this is seconds as well, 1/2 of a second. Now, if we sketch the graph, it's going to look like that, and it should. I mean, we already know all this stuff. This is omega, remember. We changed it from K to omega. This is A still, absolute value of A. And we know that T is 2 pi over omega, or 2 pi over K as we learned before. But now we're actually applying it to simple harmonic motion. Now, sound. Let's talk about sound with simple harmonic motion. Sound is produced by a regular variation in air pressure from normal pressure. If it varies in simple harmonic motion, then we have a pure sound or a pure tone. The tone of the sound depends on the frequency. The loudness depends on the amplitude. Now, we've talked about that before in class. Now we're actually going to use it. If a sousaphone player plays the note E and sustains that sound for some time, for a pure E, the variation in pressure from normal air pressure is given by this formula, where V is measured in pounds per square inch and T is measured in seconds. What's the amplitude, period, and frequency of that note being played? Well, A would be 0.2 inches, again, because we're square inches. Period would be 2 pi over 80 pi, which is 1/40th of a second. So it would vibrate at 1/40th of a second. Now our frequency would be the reciprocal of that, which is what we call 40 hertz, which means there would be 40 waves pass by in a second. And what would that look like? It would look like that equation. So the frequency would be 40. The period is short. It's only 1/40th of a second. So from there to there, 1/40th of a second. And the amplitude, well, it's not very loud. 0.2, what do we say, inches? It wouldn't be loudness then, would it? Air pressure. Okay, because we're talking about air pressure here. So amplitude would be in inches. Okay, so let's say the player increases the loudness, so the amplitude increases. So we would replace, So we would replace the number 0.2 by a larger number. Now, if the note is flat, now think about this, the frequency is decrease. Thus, the coefficient of T would be less than 80 pi. Now, if it's sharp, it's a little higher, it would be more than 80 pi, just a little bit, okay? And then we get simple harmonic motion. Now, in general, we can talk about these simple harmonic motions like we did earlier, as far as the sine and cosine with vertical and horizontal shifts. Taking a video. So we're going to look at Two equations here. Y equals A sine omega t minus c plus b, and y equals A cosine omega t minus c plus b. But it's exactly what we studied before. The vertical shift is your midline again. That's B. Your horizontal shift is C. And then our phase shift is C divided by omega, which we did before with K. Okay? So the horizontal shift indicates the position of the object at T. So you can see on A, it's been shifted over C to the right. Well, that makes sense, remember? Because we go opposite direction in parentheses. On this one, we have a move to the right C again. That's exactly what we just talked about. And then our period, 2 pi, okay? That's what we would expect. Now, let's talk about delta Cephei. I'm not sure how to pronounce it. I should have looked that up for us. But a variable star is one whose brightness alternately increases and decreases. And this star, the time between periods of maximum brightness is 5.4 days. The average brightness or magnitude of the star is 4.0, and its brightness varies by plus or minus 0.35 magnitude. Now we're going to find the function that illustrates this. Okay, well, the magnitude then must be A. So here's the equation. So the magnitude must be A. So A would be 0.35. Now we need to find omega. Okay, well, omega is 2 pi over our time. Well, what is our time? 5.4 days. So 2 pi over 5.4, we're going to go ahead and put it in decimals. I believe that's about 1.16. Since the brightness varies from an average value of 4 magnitudes, we're going to shift it up 4, so that's going to be B. Now we got to find C, but a cosine curve achieves its maximum at 0. So I believe if C is 0, we would just be alternating perfectly. We don't really have a C then. So that would be our equation. 0.35 cosine 1.16t plus 4. I got a few too many parentheses there. If we look at the graph, that's what she'd look like right there. 5.4 days. It would oscillate between 3.65 and 4.35, and it's a cosine curve. They told us it was. So it starts up here. We don't have a horizontal shift of any kind. Another simple harmonic motion generator is alternating current generators, okay, AC. Alternating current is produced when an armature rotates about its axis in a magnetic field. And this is a simple generator right here. We have the north, we have the south magnets, and the wire in between. And that would be alternating current. As the wire passes through the magnetic field, E, a voltage, is generated in the wire. Now that formula could be written as E of t equals E naught, which means the beginning, cosine omega t. So E naught is the maximum voltage produced, which depends on the strength of the magnetic field, and omega divided by 2 pi is the number of revolutions per second of the armature, or the frequency. So ordinarily, 110 volt household alternating current goes from 155 volts to negative 155 volts at 60 hertz. Okay, interesting. Find an equation that describes this variation in voltage. All right, so our omega we know is 60. Omega over 2 pi is 60. So omega then is 2 pi times 60, which is 120 pi. There's our omega. Then let's take t equals 0, and when the voltage is plus 155 V, then 155 cosine 120 pi t would be our equation. So all we're doing is talk, and I'm going to tell you right now, electricity you're going to get into in Physics 2 in college, if that's what you choose to do, and it's hard. I am not a big fan of electricity. It's tough. All right, now damped motion. Now what is this damped motion business? Okay. Eventually a spring, if you think about it, eventually it's going to stop going the same distance as far as the going up and down. It's still going to do the same time period, but the amplitude is going to decrease. And we can do this with the generator if we have Java on our computers, which we don't. But I'm going to try to show you in class how a simple harmonic generator can be made a damped motion generator. But think about this. When you swing as a child, you don't know how really, especially when you're like 2 and 3 and we put you in the baby seat, we push you and then you just go back and forth. You are modeling simple harmonic motion until you start, gravity is going to make you not go as high forward and backward until you come to a complete stop. So that's called damped harmonic motion because we damp that amplitude. So in this formula, it looks complex. It is. Just take it for what it's worth and plug in numbers. That's all we're going to do. C is what we call the damping constant. K is the initial amplitude where we start, and 2 pi over omega, again, is the period. So here's an example of damped harmonic motion. Y equals sine a pi t would look like this, right? But if we have y equal e to the negative t sine a pi t, it would be damping. Same formula. The only thing we've changed is the a and k. In this case, a times k would be 1. But in this case, it's e to the negative t. And that would slow it down to be damped. And we're going to do some of these, if you're in class, we're going to do some of these on our calculator as well. All right, 2 mass spring systems are experiencing damped harmonic motion, both at 0.5 cycles per second and both with an initial maximum displacement of 10 centimeters. The first have a damping constant of 0.5, and the second has a damping constant of 0.1. All right. So, where are we? It says find the we got to find that to model the motion in each case. Now remember, K is our initial displacement. So what is our initial displacement at time 0? 10, right? So K is 10. So that would mean that we would need to find, let's see, so it'd be K, G of t, K is 10, e to the negative. Now we need to find C, don't we? Well, the damping constant of the first one is 0.5. And I'm going to we'll call it G sub 1. We'll call this in G sub 2. This is also 10e, but it's negative 0.01 t. And then cosine omega t. Well, we got to find omega, don't we? Okay, so how do we find omega? Omega, let's see. Let's read the problem again. Oh, right here. Here's the frequency. So the frequency is 0.5. So omega is 2 pi times 0.5, right? Because, let's see, frequency equals 2 pi over omega. No, I did that wrong. My bad. T equals 2 pi over omega. And we know that frequency Oh, I did that wrong again. I got to get frequency. Frequency is omega over 2 pi. There we go. So we would multiply by 2 pi. There's our equation. So 2 pi times frequency. So we take, yeah, I was right, 2 pi times 0.5, because frequency is 0.5, which I believe would be pi. So that would be pi t, and that would be pi t. And there's our equations. Now, if you graph those two functions, they're going to look like this. And you can see that since this damping factor is more than this damping factor, it comes to a halt way sooner than this one does. It dies down much, much faster. Now, we can do this on our calculators, and it's a lot of fun, and we will. But now let's look at a violin and a string that's pulled a distance of 0.5 centimeters from its rest position. The damping constant C for this note G is determined to be 1.4. So there's our C. Here's our A. Suppose that the note produced is a pure G, a frequency of 200 hertz. Find an equation that describes the motion of the point at which the string was plucked. Okay? Well, back to our damping formula. It's going to look like that. Okay? First of all, we know A, or K in this case, is 0.5. So we can go 0.5 E. We know our damping constant is 1.4. So we can put that in there, negative C. And then there's T. And then there's cosine. And now we got to find omega. But omega, remember, is 2 pi times F, like it was up here. 2 pi times F. So that's going to be, 400 pi. 2 pi times 200. So 400 pi T. And that would be our string. Okay, so yeah, so that would be the equation of our damped motion of our vibrating violin string for the note of G. Now, the last thing we're going to talk about is phase and phase difference. Now, when two objects are moving in simple harmonic motion with the same frequency, it's often important to determine whether objects are moving together or by how much their motions are differing. So let's consider a specific example. Suppose that we have an object rotating along the unit circle and a height y of the object at time t is given by this. When t is 0, then y equals sine of negative b. Makes perfect sense. This means the motion starts at an angle b, as shown in figure 14. Okay? So there's the graph of y equals sine kt minus b. We have a horizontal shift of b over k. Yes, because we're going to factor out k. So we're going to shift it over. Okay. Now, we can view the starting point in two ways. As the angle between P and Q on the unit circle, or as the time required for P to catch up to Q. The angle B is called the phase, or phase angle. To find the time required, we factor out K, which is what we've been doing, right? So P catches up to Q when T is B over K. So this is our horizontal shift on the T axis. Now this is what we've been calling phase shifts this whole time. So that horizontal shift and phase shift is basically the B over K. Now this gets into waves, and if waves are out of phase. So if you look at these guys right here, these are objects in simple harmonic motion. Okay, stay with me here. And we want to know the amplitude, period, phase, and horizontal shift. So remember, phase is simply B in this case. So A, let's see, amplitude's 10, period is 2 pi over 3, the phase is pi over 6, and the horizontal shift is pi over 18, right? You factor out a 3. Versus this one, A is 10, P is 2 pi over 3, the phase is pi over 2. Now what's the horizontal shift? Pi over 6. So these are out of phase. Pi over 6, pi over 2. And then the last one, again, amplitude's 10, period's 2 pi over 3. But now we factor out a 3, it's 23 pi over 18. So if we sketch all the curves on the same axes, it looks like this. And you can see that the periods are all the same, the amplitudes are all the same, but they're just slightly out of phase, just a tad. But you'll know, oh, except for this one, right? That one ends up being the same graph because, let's see, the phase difference we would subtract. Now, I'm not concerned at all about the phase differences and things like that. But if we find the phase difference between the two curves, the first one is pi over 6 minus 2 pi over, well, what's the first one? Oh, y1, y2. What did we get on y2? Pi over 2, right? Oh, pi over 2 minus pi over 6, sorry. So we're going between these two. So pi over 2 minus pi over 6, y1, y2, that's it. So that'd be pi over 3 would be our phase shift. Our phase difference, sorry. And then between 1 and 3, it'd be 23 pi over 18. No, 23 pi over 6 minus pi over 6, which was 22 pi over 6. Or was that negative? Oh, it was negative. Oh, shoot. So it was negative. Oh, my bad. So negative 23. Got to get my stuff together here. Hold on a second. So we would have pi over 6, y1 and y3, minus negative 23 pi over 6. There we go. So that's 24 pi over 6, which is 4 pi. There we go. So it's the same graph because 2 times 2 pi is the same. So they're in phase. So this one and this one are actually the same graph. They're in phase, but this one is out of phase with the other two. So that's what that phase difference means. And really, we're not going to really talk about that much in our WebAssign. I know this was a long lesson. If you have questions, please ask. The main thing to understand is that we can apply everything we've done now using simple harmonic motion.